तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we shall continue our discussion on MOS logic circuits. The circuits we were discussing last time was the dynamic CMOS logic circuits or clocked CMOS logic circuits. Okay. So, we had seen that if you have a circuit like this, that is, you have a PMOS, then an N block, and then an NMOS transistor. Okay, and you have a clock, okay, which is connected to this circuit, okay, and this is the N block, which consists only of NMOS transistors, and the inputs are fed to the N block. Okay, for example, if we have a NAND gate, we had taken that example last class. That is, you have two NMOS transistors here. Okay, then when the clock is low, okay, when the clock is low, what happens is this NMOS is off and the PMOS is on, and you have a load capacitance, say, okay, which may be the input capacitance of the next stage gates. Okay, what happens is the output voltage is charged to VDD. All right. So, this is called the pre-charge phase. So, when phi is 0, phi is low, say, you have the pre-charge phase. Okay, you are pre-charging the output. Okay, and then when phi goes high, what happens is the PMOS goes off. Okay, so there is no connection to VDD. The NMOS turns on. Okay, so there is a possible path to ground, provided that these transistors, the N block, as a block, provides a connection to ground. Okay, so in this case, if you have two inputs A and B, only when A and B is high, okay, then only there is a path to ground. Okay, so when A and B is high, then only the output is 0. Okay, so this is a NAND gate. So the capacitance gets discharged. Okay, so when phi is high, this is the evaluate phase. That is, when phi is high, the output, basically you have the logic, you generate the logic function in the evaluate phase, that is when phi is high. Okay, so this is a clocked CMOS circuit. The obvious advantage is that here, whatever be the complexity of the gate, okay, if you have, say, n number of inputs, okay, you have n number of, in a normal CMOS, you will have twice n number of transistors, whereas here it is going to be just n plus 2. Okay, so basically here you have the lower n block of a CMOS. Okay, in a CMOS you have the lower n block and the upper p block, okay, of transistors. So here you have just the n block of the CMOS. Okay, all right. So this is dynamic CMOS. Okay, but this circuit has certain disadvantages. Suppose, for example, if you have this particular circuit is driving a similar dynamic CMOS gate. Okay, for example, you have another, say, n block, and you have a similar circuit. All right, another clock here, the same clock is fed here, and this is going as input to this n block, okay, where you have NMOS transistors. Okay, all right. So what is going to happen is, when the clock is low, okay, that is the pre-charge phase, what is going to happen is this input capacitance of this transistor here, okay, in the second stage, that is going to be charged to VDD. All right. So, okay. So, what is going to happen now? Suppose this clock goes from low to high. So, for this gate, you are going to the evaluate phase from the pre-charge phase. So, at this instant when the clock goes from low to high, okay, provided that again you have a NAND gate and this inputs are all coming from previous stages, okay, all the inputs to these gates are going to be high. Okay. So, before this, so all the clocks go high simultaneously. So, before this input has time to react to the changes in the previous gate, you know, first this output must change and then effectively the output, the other output must change. Basically, if you have something like this, this is you have a NAND gate, say, all right, 2 NAND gates, and then it is like this. Okay. So, depending on the inputs here, these outputs will change. Okay. So, once this output changes, then depending on this, okay, which is the input here, the next output is going to change. Okay. So, suppose so basically what happens here is that these inputs are high at the time when the clock goes high. So, before it has time to react, what is going to happen is there is, so again here this in the pre-charge phase you have charged this capacitance. So, there is a path to ground immediately, okay, because these transistors are all on. Okay. So, this capacitance is going to get discharged. Okay. All right, because this inputs are all charged to high, all these transistors are on, okay, at the beginning of the evaluate phase. Okay. So, that is going to create problems, because once this charge is discharged, there is no way in the evaluate phase the output can go high. All right. So, what so the way to circumvent this problem is we have to ensure that at this instant when the clock goes high, that is the start of the evaluate phase, all these transistors in the N block, they must be off. Okay. So, how do you do that? We just put an inverter here. Okay. An inverter is introduced here, okay, at the output of this circuit. So, what happens is basically now when in the pre-charge phase, the input capacitance of the inverter is charged to high, all right. So, the output is always low, okay, and this output is going to the inputs of the next stages. So, in the pre-charge phase, all the inputs of the N block, they are low. So, all these transistors are basically off, all the NMOS transistors in the N block, they are off. Okay. All right. So, this is okay, true for all the gates here. Now, what happens is, suppose you have stages like this. Okay. Suppose A and B is high, goes high, A and B goes high, then what happens is this the output which was high here in the pre-charge phase, this capacitance gets discharged through this path. Okay. So, this high goes low, then the output of this inverter goes high. So, then only this transistor turns on. Okay. And suppose this input is coming from a similar gate, then only it has a chance to turn on, and once it turns on, then only this capacitance, okay, that the input of this inverter can get discharged. Okay. So, the input of the capacitance of the inverter was charged to VDD during the pre-charge phase, then only it gets a chance to discharge. All right. So, you see what happens is, first this output of the first stage will change, okay, and depending on that, okay, the next state will change like that. Okay. So, this particular circuit is called a domino CMOS. Okay, circuit, because the changes happen one after the other. Okay. first stage changes, then depending on that the next stage will change, and so on and so forth. Okay? So, this is the circuit of a domino CMOS. Now, well, one can really avoid this inverter by using what is called an NP CMOS. Okay. So, where what you do is the next block, okay, is basically made up of PMOS transistors. Okay. The circuit is going to be something like this. Again, what you have is a PMOS transistor here. This is actually a P block, not an N block. It's a P block that is consisting of PMOS transistors. Okay, and this you have the NMOS transistor. So, here instead of phi bar is applied, the complement of phi is applied, and so this output here can be fed directly as input here. Okay, and then again you have the N block. So, the next stages are all N block. So, this is VDD. So, the output from here, okay, it comes from here, the output is from here, goes to N block. Okay. Again you have similar, this is PMOS, this is NMOS. Okay. So, this output is taken from here. So, what happens is, if you just look at it now, when phi is low, it is again the pre-charge phase. Okay. So, what is going to happen? All the outputs capacitances are going to be charged. Okay. So, the output is not it is just the pre-charge value, it is not the exact output of the logic circuit. So, in the pre-charge phase, when this goes low, here all the outputs are high, okay, and this is going to the P block. So, all the PMOS transistor inputs are high. So, all the PMOS transistors are off. Okay. Now, here what happens is, this is you have applied phi bar. So, when phi is low, phi bar is high. So, this NMOS transistor is on. Okay. So, the output of the P block is low. Okay. So, all the N block inputs, the inputs of the NMOS N block, they are all low. So, all the inputs, all the NMOS transistors in the N block, they are off. Okay. So, basically it is like this, that to ensure that this works properly, at the beginning of the evaluate phase, okay, all the transistors in the P block or the N block, they must be off, and then depending on the inputs they can turn on. Okay. They can turn on, and if they turn on, then only the output changes. Okay. Otherwise it retains the pre-charge value, okay, that is whatever was the output during the pre-charge phase. Okay. All right. So, what happens now is, suppose if you have this configuration here, when in the evaluate phase, okay, in the evaluate phase the phi goes high, that means the NMOS transistor here turns on. Okay. So, depending on this input here, the output can be discharged. Okay. This charge means the output here. So, it goes to the input of a PMOS transistor. Okay. So, that PMOS transistor input can go low, okay, which means that PMOS transistor can turn on. Okay. And so, if the PMOS transistor turns on, you say there are a number of PMOS transistors in this P block, and suppose this P block as a whole turns on, that is, it is conducting. So, what can happen is, this output was basically low. All right. So, if this is conducting, so in this phase, okay, this NMOS is off and the PMOS is on, okay, because this is phi bar. Okay. So, if this is conducting, the output here, this is off. Okay. So, this can charge to VDD. So, this output of this P block, okay, here can go up to VDD, which means that this can turn on the next N block transistors. Okay. So, again it is like a wave, you know. So, first these transistors have to turn on, and depending on this, okay, this can turn on the next block transistors, okay, and then if it turns on the next block, then the next block can turn on and the output can change. Okay. So, this type of devices, this type of logic gates, okay, they are clocked logic gates, and they are the advantage here is, of course, that you save a lot in terms of transistors and equivalently in terms of area. Okay. So, these are quite popular nowadays. Okay. One disadvantage you can say is that one point to be noted is that in this case, okay, there is a limit on the lower frequency of operation. Okay. That is, you can operate the circuit above a certain frequency. This clock frequency cannot be made too low. Okay. The reason is like this, that the output, it basically works on the principle that during the pre-charge phase you are charging the output, charging the capacitance, all right, the output capacitance of this gate, which is the input capacitance for the next stage. Okay. And then if this circuit is not this block is not on, the charge is retained. Okay. And so the output voltage retains its previous value. But all these capacitances are not ideal capacitances. There are leakage paths. Okay. And so the output charge, okay, is going to decay with time. Okay. So you have to, this pre-charge evaluate phase must be quick enough, okay, so that before it the charge decays, you have the next pre-charge and evaluate. Okay. This evaluate phase or the pre-charge cannot be too long. Okay. Otherwise the output voltage is going to change. Okay. For example, this P block input, okay, what happens is when you charge this input goes high in the pre-charge phase, okay, and then suppose this NAND gate, one of the inputs is 0. Okay. So this is off. Okay. This P block input, which was charged to high, is going to remain high because there is no path to ground. But so that is the expected output of this logic circuit. Okay. But because of some leakage paths, this output can decay with time. Okay. All right. So if the evaluate phase is too long, okay, slowly the output voltage is going to fall. Okay. So the period has to be short. Okay. So all these circuits, they have a lower limit, okay, on the frequency of operation. Okay. That is, you have to operate it above a certain frequency, which is not really a big disadvantage, because nowadays the clock frequencies of operation are quite high, and so, okay, this is not really a disadvantage. I would just like to say that, well, this type of circuit, okay, it is although you have a clock and it may seem that you are actually you require an additional resource here to get this circuit working, but it is not really so. See, if you look at any system, okay, digital system, which consists of combinational and sequential logic circuits, okay. For example, if you take the finite state machine model, okay, which is can be used for any digital system, okay. Say what you generally have is you have a set of inputs, okay, then you have a set of outputs, okay. This is a combinational logic, okay, circuit, and then what you have is you have a set of flip flops, okay. So from here you generate the states of the system, okay, and you feed it to the flip flops, okay, and from here this goes in as the input to the combinational logic. So this is this can be treated as a model of digital system, okay. So basically here in the flip flops you require a clock, okay, and this clock can be, okay, it can be a negative edge triggered flip flop. So the changes, whatever they take place, okay, they take place in the negative edge, of the clock pulse. Okay. So, when the clock goes from high to low. Now, suppose here you have a digital circuit, a dynamic logic circuit, okay, where the changes take place, the evaluate phase is when the clock goes high. Okay. So, what happens is the similar circuit as we have already seen. Okay. So, what happens is when the clock is low, it is in the pre-charge phase. Okay. So, the output here, okay, is comes here, but it is not going to affect the flip flops because the clock is low. Okay. Now, when the clock goes high, you have the evaluate phase. Okay, that during this time the output of this combinational logic block is going to change depending on the inputs to that combinational block. Okay. So, the inputs, so the output is ready when the clock is high, and then what happens is then the clock goes from high to low. Then depending on what is the inputs, you see the output of the combinational block is actually fed as input to the flip flops. So, when the clock goes low, okay, depending on the inputs to the flip flops, the output changes. All right, and so the output changes, okay, but then the clock is low. So, when the output changes here, but the clock is low. Okay. So, again this is the pre-charge phase, but the output of the flip flops is retained, okay, till the next negative edge of the clock pulse. So, this inputs will be there, okay, here ready, and again you have the inputs to the system. Okay. So, when the clock goes high, again you have the inputs ready. So, depending on that, again the output of the combinational logic is going to change, okay, and then it's going to again affect the flip flops. Okay. So, you see that it is a perfectly viable system. Okay. You use the same clock for the combinational logic part as well as the flip flops. Okay. So, basically you are not there is no extra overhead actually for having this clock here. All right. So, the same clock can be used for the combinational logic. What you gain here is if you use the CMOS, normal CMOS circuit, okay, you would require twice the number of transistors. Here you require almost half the number of transistors, and you all the advantages of CMOS are still there. Okay. So, you do not lose out anything. Okay. So, this is actually a very popular form of circuit, okay, which draws the advantages of the CMOS logic. At the same time, the disadvantage of CMOS of having too many transistors is reduced. Okay. All right. So, the next form of circuits which we shall take up for discussion regarding MOS logic is the circuits which come under this category of pass transistor logic. Okay. What is a pass transistor? A pass transistor is nothing but, say, an NMOS transistor. Okay. Now, why is it called a pass transistor? It is called a pass transistor because when the gate voltage of this NMOS is high, okay, then it behaves as a on switch. You can consider this as a switch. Basically, in a pass transistor logic, we consider this as a switch. So, when the gate voltage is high, this transistor is on switch. It's just like a switch. So, whatever is the input is passed on to the output, and when this gate voltage is low, this behaves as an off switch. Okay. So, there is no connection between the input and the output. Okay. So, that is the basic property of this. Now, this can be used to realize logic gates. Okay. For example, if I say that this input is A and here this is B, okay, what is the logic at the output? Well, if B is high, then the output is A. All right. So, we can say that, well, but that does not give us all the conditions. Okay. So, basically what we have to do is we have another transistor here. This input is B, the complement of B. Okay. So, just draw it properly. So this is B, bar, okay, and we make this go to ground. Okay. All right. So, now what do you have? When B is high, output is A. Okay, that means if A is also high, output is 1. Okay, that when both are high, then only the output is 1. If B is high, A is 0, output is 0. When B is 0, okay, then this is off. Okay, this is on. Okay, so output is 0. Okay, so only when A and B are both high, okay, then only the output is high. So it is a AND gate. So you have realized an AND gate. So with the pass transistors, okay, the advantage you can see very well is that you have just used 2 transistors, all right, and also, well, this power dissipation is also, you can say that effectively this does not consume any power because it's not connected to power supply. Okay, it's just using the power in the inputs. Okay, so it is it is very low power dissipation circuit. Okay, as well as the advantage is you have very high density in the sense that you can realize logic functions using very few transistors. Okay, so both these advantages, okay, are what you require in a large scale integration, for large scale integration. Okay, so this circuit, so this concept of logic gates is ideally suited for large scale integration. Okay, so this is one example we have given, but always we must be careful when we use this for logic circuits. We have seen this, you cannot just say this is A and B, okay, because when B is 0, if we just use this block here, okay, all right, when B is 0, the output would be undefined. Okay, so you must always have you must always take into account that all the possible input combinations are accounted for. Okay, so that is one constraint you have to think of. The other point is, suppose this B is high, all right, here. So that is, this high means VDD. Okay, and suppose A is also high. Okay, VDD. Okay, now what is going to be the output? Okay, initially say output was 0. So when this turns on, okay, the output, again you think of it as a capacitance, some capacitance here. Okay, all right. So this output has to be charged to VDD. So the output rises. Okay, basically you can consider this as a resistance here. All right, this transistor, as you can consider it as a resistance. When this transistor turns on, it is a very low resistance, and when this transistor is off, it is a very high resistance. Okay, so when this is a low resistance, this capacitance is going to charge with an RC time constant. Okay, slowly it approaches VDD. Okay, but when it reaches VDD minus VT, okay, what happens is, so this is basically the drain and this is the source, because this is a higher potential. Okay, so when this source voltage reaches VDD minus VT, okay, then this transistor cuts off. Okay, all right, because it cannot rise any further, because it cannot supply any more current once the gate to source voltage falls below VT. Okay, so there is a drop of VT, okay, for this pass transistors. Okay, all right, so the output voltage can only rise till VDD minus VT or VG minus VT, whatever is the gate voltage. Okay, so this is a drop. So you have better switches, okay, to realize this same logic, what is called the transmission gates. Okay. Okay, a transmission gate consists of an NMOS and a PMOS. This is an NMOS. You have an inverter here. The two gate voltages are complements of each other, all right, and this, suppose this is the input, the other one is the output. Okay. Now, so this is the control input here. Okay. Now, suppose you have a high here, VDD, as we had in the previous case, at the gate of the NMOS. Okay. The voltage at the gate of the PMOS is going to be 0, okay, or ground, okay, say, all right, because this is the output of an inverter coming here. So, the inverter input is VDD, okay, the output is going to be ground, all right. So, what happens here? What happens is, suppose you have an input here high, all right, then what happens? This is VDD. What was happening was, as this output voltage was charging up, okay, the gate to source voltage of the NMOS was going was reducing, okay, all right, the gate to source voltage was reducing. So, what happens is that the effective resistance of the NMOS transistor is increasing, all right, and so it requires more and more time to charge this output capacitance, and finally, when the output voltage reached VDD minus VT, this would be turned off, okay. But here what happens is, for this PMOS, this gate voltage is 0 volts, okay, and this is the source here, okay, the higher potential. So, this is the source which is at VDD, okay. So, this one would always be on, okay, and so this output, okay, is always going to be going all the way up to VDD, all right. So, in fact, if you look at it this way, that is, suppose the input, okay, you have a VDD here, okay, and the input is going from, say, is going from low to high, okay. What you would expect if it is a perfect switch is the output would also go from low to high, change like this, okay. Now, if you plot the resistance, okay, versus, say, V in or V out, okay, for the, say, the NMOS transistor, okay, what is happening is, as the voltage goes higher and higher, the gate to source voltage is reducing. So, the resistance of the NMOS, you know, it will go up like this, okay. So, I shall say R on for the NMOS, okay, all right. And now, for the PMOS, what happens? Initially, the voltage was 0 here, okay, at the input, okay. So, the PMOS was off because the gate to source voltage was 0, but as this voltage is rising, okay, the gate to source voltage is becoming more and more negative. Gate is 0, the source is becoming more and more positive. So, the gate to source voltage is becoming more and more negative, okay. So, for the PMOS, since the gate to source voltage is becoming more and more negative, okay, the resistance is falling. So, if you plot that for that PMOS, you know, you will have something like this, R on for the PMOS, okay. Okay. So, the effective resistance which you have is actually the parallel combination of these two resistances. So, the effective resistance, you take the parallel combination, is going to be something like this maybe, okay. I will call this R effective, say. So, the effective resistance in a transmission gate is almost going to be a constant because of the parallel combination of the NMOS and PMOS, okay. So, this is a more ideal switch compared to the pass transistor, okay, and it is the resistance is not going to alter depending on the input and output voltages, okay. So, this transmission gate may be used in place of a pass transistor, all right, and this is more compatible for CMOS technology, as you can see, because you have both PMOS and NMOS transistors, okay. So, when you are making a CMOS circuit, okay, you can have this type of transmission gates, okay, all right. So, basically we shall take up some pass transistor circuits to show that actually how you can realize complicated logic circuits using very few transistors. I shall draw the circuits using just an NMOS pass transistor, but all these circuits can be realized using transmission gates by just replacing the pass transistor using transmission gates. Well, the classic example of this use of this pass transistor logic is in the multiplexer circuit. Okay, multiplexer, you know, has got if you have n control inputs, you have 2 to the power n inputs and 1 output. Okay, so it is just like this. Okay, so this is, you have n control inputs, say, and you have 2 to the power n inputs and 1 output. Okay, and depending on the combination and the control inputs, okay, one of the inputs is connected to the output. The output, you get the value corresponding to one of these inputs. Okay, so that is a multiplexer. So how do you realize it? Using pass transistors. It is very simple. So normally if you used gates to realize that, you would require a large number of gates. So suppose I want just say a 4 to 1 multiplexer, that is, you have 4 inputs, and just so you would require 2 control inputs, okay, to realize this 4 to 1 multiplexer. So let the control inputs be called A and B. So suppose this input is A, this is A bar, this is again A, this is A bar. Okay, this is B, this is B bar. Okay, so this is input 0, input 1, input 2, input 3. I think I should write it the other way around, that is 0, 1, 2, 3. Okay. So when A is 0, B is 0, 0, 0, what happens is A bar is high, B bar is high. Okay. So this input here is connected to the output. You see that this line is connected. All other lines, okay, all other inputs would be disconnected from the output. Okay, all other inputs are disconnected. When you have 0, 1, okay, that is A is 0, B is 1. Okay, all right. So okay, I think, okay, then what happens is, all right, this goes connected. Okay, that is when A is 0, this is turns on. Okay, and B is 1, it goes like this. Okay, so okay, so when for example A and B are both high, then this path is connected. Okay, so you see that depending on the 4 possible combinations of A and B, one of the inputs is connected to the output. Okay, and so you have a multiplexer using just 6 transistors like this. Okay, you would require many more transistors if you were to realize this using gates. Okay. Then the other circuit, for example, if you take another circuit, say a decoder circuit. You know what a decoder is? Again, you have how many inputs? You have n inputs, and you have 2 to the power n outputs. Okay, and depending on the combination here, one of these outputs is going to be high. Okay, so if it is 0, if you have say 2, just take the simplest case of 2 inputs and 4 outputs. For 0, 0, one line is going to go high, all the other output lines are going to be low. Okay, for 0, 1, another line is going to go high, like that. Okay, so how do you realize that using pass transistors? So I just so basically what you have is, in a decoder, say if you have 2 inputs, say A and B, you have 4 outputs. So you have A bar, B bar, A bar, B, A, B bar, A, B. There are 4 possible combinations. Okay, so depending on the input combination, only one of them is going to be high, all other outputs are going to be low. Okay. So, you can realize that using pass transistors, very simple configuration. You take VDD, then you have A, this is the A bar line, this is the B line, B bar line. Okay. So, this is A, this is B. So, this output here is going to be high when A and B are both high. Okay? All right. But again, this is not complete, because you have to ensure that when A, because when A and B are, one of them is 0, the output is undefined. Okay? So, you have to ensure that whether A or B goes low, okay, the output must go low. Okay? So, you require 2 additional transistors here. Okay? From here, okay, you make this ground. All right, this is connected to B bar. Okay, so when B goes low, B bar goes high, this transistor turns on. Okay, when this transistor turns on, this output, okay, must go low. Okay, so this is connected here. Okay, this output goes low. Also, when A goes low, all right, this output must go low. So you have this connection here. Okay, these 2 transistors ensure that when A or B goes low, okay, the output is going to go low. Only when A and B goes high, the output goes high. So this gives you AB. Okay. Similarly, you can have other combinations. For example, A bar B. So this is VDD here. Okay. So if you have A bar B, you put like this. Okay, this is A bar B. So again, you must ensure that for the other cases, okay, the output voltage goes to ground. So you have another set of 2 NMOS transistors here. Okay, so this is ground here. So this must be connected to the output. Okay, so of course you can draw the circuit for the other 2 combinations, AB bar and A bar B bar. The advantage here is, you see, we had already seen that in NMOS technology, you can have the gate made of polysilicon, okay, and when a polysilicon line overlaps a diffusion line, you have a transistor. Okay, so you see that how easy it is, okay, to make this circuit. It requires very little area, because this line can be made of diffusion. Okay, and these are the gates, okay, of the transistors. They can be running on polysilicon. Okay, so this, it will just run like this. Okay, wherever you don't want an overlap, okay, you have to make this into metal, say, for example. Okay, all right. So you can have a very dense circuit. Okay, all right, having using a very little area. Okay, you can have a large decoder, for example, fabricated in a very small area using this particular type of circuit. Okay, pass transistors. Okay, so that is the advantage of using pass transistor logic, and also nowadays in VLSI, okay, a large part of the circuits are made out of pass transistors. Okay, because of these advantages. Finally, one more circuit I would just like to draw. Using pass transistors, that is the D flip flop. Okay, you can, how easily you can make a D flip flop. A D flip flop, you know, just a D flip flop with which is enabled when the clock is high, will behave in, will pass the input to the output when the clock is high, and when the clock is low, the previous output is going to be retained. Okay, so that is very easily realized using a pass transistor. So this is the D input, and say this is the clock here. Okay, so and you have 2 inverters. Okay, and here you put clock bar. Okay, all right. So, here when the clock goes high, okay, what happens is whatever is the D input is passed on here, and you have two inverters here, all right. So, basically the output of these two inverters is going to be the same as the input here. So, at the output you have the same as the D input, okay. But when the clock goes low, you have to retain the previous value. So, this clock, this pass transistor cuts off, this transistor turns on. So, you have two inverters, okay, connected like this in series, okay. So, whatever is the input is just it is fed back, you know. So, if this is 1, this becomes 0, this is 1. So, it is a perfectly stable system, okay, and it is going to retain whatever is stored here, all right. So, this is a D flip flop. Now, if you want sort of master slave operation, that is you want the output to change only at a particular instant and not when the clock is high, what you have to do is you have to have a second stage, okay. And here what you do is you make this clock bar, okay, and this input here is clock. So, this is going to give master slave operation, okay, because this slave flip flop, okay, operates only when clock is low, all right. So, what happens is when the clock is high, okay, whatever is the D input is can go up to here, but it cannot pass through, all right, okay. So, what is going to happen? So, this is retained here, okay. Now, when the clock goes from high to low, okay, this turns off, okay, this turns on, okay. Whatever is retained here is passed on to the output, but after that instant, okay, this clock is off, okay. So, the input will not have no further effect on the output, okay, and whatever was here is going to be retained at the output of the flip flop, okay. So, only at the instant when the clock goes from high to low, okay, the output is going to change, and after that there can be no further change, okay, because this master is going to be off when the clock is low, all right. So, this behaves as a master slave flip flop, D type flip flop, okay. So, you see again how easily you can realize this type of logic circuits using pass transistor logic, okay. And that is why it is so popular, because on one hand you save space or area, okay, using pass transistor logic, and also because of and also the power dissipation, okay, is very much reduced, number one because you are saving on a lot of circuitry, and also because pass transistors by themselves do not consume any power, okay. They are just transferring the input to the output, okay. So, that way you save a lot of power. So, both of which are required, okay, in a large scale integrated circuit, okay. So, with that we come to the end of this section on pass transistor logic, okay. In the next class we shall take up another variation of CMOS, which has become quite popular nowadays. It is bi-CMOS, okay, where actually you use bipolar transistors together with CMOS to achieve logic circuitry, okay. And the advantage of using bipolar transistors is that you can increase the speed of operation, okay. At the same time you retain all the advantages of the CMOS in a bi-CMOS, that is the low power dissipation, that is zero static power dissipation. So, the problem was initially that it was difficult to fabricate both CMOS and bipolar transistors on the same wafer, because the requirements were different. But once that problem has been sorted out, okay, it is one can really fabricate bipolar transistors and CMOS on the same wafer, okay. One can really derive the advantages of both CMOS, okay, and bipolar transistors, the drive capability of bipolar transistors in one logic circuit, okay. So, that is superior to CMOS, okay, in many ways, okay. So, we shall take up that for discussion in the next class and see some applications of bi-CMOS logic circuit.